Okay, so here's the plan for the next couple of days. If you guys forgot since yesterday, today's actually our last topic. We're done this unit, so we're now, after today, we'll have been done 3/4 of our curriculum for Chem 20, which is awesome. Tomorrow and Thursday, we're going to do labs. Okay, if I know I described this already, but I'll describe it one more time. One lab that's going to take place is a titration. Okay, and I'll demonstrate for you guys how to do a titration. Then I want you guys to try it yourself, so that it's not just on paper that you're trying to figure out the math, but you actually get some like hands-on experience. Does that make sense? While most groups are doing a titration, though, the other lab we're going to do is a percent yield by gas collection. And we'll just do that at the back table, one group at a time. The only reason why we're doing it one group at a time is I just don't have enough of those Erlenmeyer flasks with sidearms to give everybody one to do. So we'll just do it one group at a time. Does that make sense? So that's our plan for the next couple of days, and then next week is basically test week. So we'll have our quiz and our unit test next week. So, how far are you guys on the assignment? Like, I haven't started it yet. I was gonna say I've talked to a couple of you that are close to being done. Is that right? Okay. Just so you guys are forewarned, before you actually mark your own assignment, I believe it's out of 12, just so that you know. And it literally is basically you're going to have an answer like 512 grams or 13.3% yield, right? It's basically 1 mark or 0 marks, and there's only 7 questions. I know there's some A's, B's, and C's, but just so you guys are forewarned, if you want to double check your work against somebody else, it wouldn't be a bad idea because it's only out of 12. Okay, which means that any mistake you make is like a 8% loss. So, anyways, I'm just giving you the warning. The key is on the board, by the way. So, okay, let's talk our last topic here. To do that, though, I need to revisit one more time how titration works, just because I want to make sure I'm really thorough that you guys get this concept. So, what's the point of a titration? Can anybody tell me like why we would do this whole thing? That's probably the best way of putting it. Yeah, we want to try to find something's concentration. Now, there are 2 ways of finding a concentration. Way number 1, you make it yourself, right? Let's say that I wanted you to make a 1 molar solution of sodium hydroxide. If I asked you to make a 1 mole per liter solution of sodium hydroxide, what you would do is you would first need to know like what size flask you're putting it in. So let's say that it went into a 250 milliliter flask. I'd start with this 0.250 liters. I would divide by the 1 mole per liter. Oh, that's not going to do it. I'm going to times by the 1 mole per liter. I'll cancel that. And then for the last thing, you'd use the molar mass, which for sodium hydroxide is 40. And then that would tell you how many grams to use. And then you would put that into your flask and you'd fill it up with water. Does that make sense? That is if you had to make it yourself. And yesterday we had a word we used to describe that. You guys remember what it was called when you make the solution yourself from a solid? A standard solution, which you're making from what's known as a primary standard. Okay, so that's one way of making a solution. You make it yourself. You weigh out a mass. You put it into the flask. You fill up with water up to the line. You stir it, and you kind of do like what we did in our first unit. That's option 1. But option 2 is if you already have a pre-made solution, you're going to do a titration, which is what we're going to do in our lab starting tomorrow. What you're going to do is you're going to take the long, thin tube called the burette, and you don't have to do it this way, but standard way of doing it is you put a base inside the burette. And then what you do is you take a acid and you put a small measured amount of acid in an Erlenmeyer flask below it. You also add 3 drops of indicator, and typically we use phenolphthalein. What I'm going to talk about today, though, is that we don't actually have to use phenolphthalein. It's just phenolphthalein is quite nice. One of the reasons why we like phenolphthalein, I'll even write that out, phenolphthalein, is that it goes from 8.2 to 10, and it goes from colorless to pink, which means that as your drop of base happens to hit the acid right here, it turns pink, right? But what we're hopefully going to visualize is that immediately after it turns pink, it's also going to touch the acid as well. And as it touches the acid, it will neutralize and go colorless. Rebecca? Well, what ends up happening is that's why you always want to go 1 drop more. That makes sense because at that equivalence point, you'd have exactly the same amount of acid and base, which would be a pH of 7. As soon as you add one more drop, it should then make the concentration jump from like a pH of 7 to like 8 or 9, and then it would turn pink. And it would only take one drop. I'm actually going to show you. That's actually part of my lesson today. Is that concept? Does that make sense to you? Let me say that to everybody else. The idea is that when exactly the right amount of base, like from here to here, has been poured into the acid, and it's exactly neutralized, the pH, I agree, would be 7 technically. But then as soon as you add one extra drop of base, the pH is all of a sudden going to go from being neutral to being clearly basic. Does that make sense? And so, I mean, I don't know whether the pH is going to go to 8 or 9 or 10, but like it's clearly going to jump from being neutral with one extra drop to being higher, and then that's what's going to cause it to be just faintly pink. If you add 2 or 3 drops extra, you're adding too much. Okay, well let me go through these notes I've got today then. What I just described there can actually be graphed. Okay, when you're adding your amount of base to your acid, and we're trying to figure out what the pH of the solution is down below here, we can actually graph that. And before you look at the graph that's on the slide below, which you can already see, let's just talk through what you'd expect. As you start with acid down here at the bottom, what's the typical pH of an acid? Low, like 1 or 2 maybe. Does that make sense? Now, as I add base to the solution, what's going to happen to that pH? It's going to rise, but is it still going to be acidic? Well, yeah, because as you add 1 or 2 drops of base at a time, it neutralizes part of the acid. It just means you have less acid, but it's still going to be acidic. So for the longest time, you're going to have a pH that's going to be very low. And then eventually you're going to reach a point where all of your limiting acid, because remember, this is what limits you, right? Your acid, is eventually going to, quote unquote, run out. And then, like I was saying with Rebecca for a second there, for one moment in time, the pH should be exactly 7. Right? Because what should happen is that equivalence point should be reached, where you have the exact same amount of base as you had acid down there, and it's exactly neutral. The pH would then be 7. Well, what happens if you accidentally keep adding more base? Well, then the pH will then jump well above 7 to 8 or 9 or 10. Now, let's say you just keep dumping in excess base. Let's say you're supposed to use this much, but you actually use a whole lot more. Will the pH eventually get to be 19 or 57 or 103? Doesn't really work that way. It's not like it's linear where it will continue on that trajectory. Like at some point it's going to like limit out. For those of you guys who are in my Math 30-1 class, the word we would use is an asymptote. Actually 20-1s, we've done asymptotes as well. You actually kind of have an asymptote on this graph. And so I'd like to actually show you what this graph might look like here. This one's actually backwards though. This is what would happen is if you added an acid to a base. So imagine we flip the scenario though for this particular graph here. Let's say that you started with a base. What would the pH of a base be? Well, really high, right? And as you add acid drop by drop, the pH is going to start to decrease a little bit because it becomes more acidic. Well, then what's going to happen is right here, at this point right here, this is that equivalence point. Where ideally, it goes from being either acid to then being neutral to then if you add even 1 or 2 more drops, it should instantly become a base. Because at this point right here, the amount of acid and base should be equal. More specifically, I know I'm kind of in broad terms saying this is the equivalence point, but I can narrow it down way better than just like this box. I don't want to take a stab at saying where the equivalence point should exactly be. Yeah, when the pH is 7 right here, this is the equivalence point. Or ideally, for one brief moment in time, you have exactly as much acid as you have base. Does that make sense? But as soon as you add one more drop, it all of a sudden changes, and that's where the color change takes place. So this is actually a graph of a different scenario. This would be where you would start in your tube right here. You'd be starting with acid up here, and you'd be using a base down here instead. Okay, like we don't have to go base acid. You could flip them around, but we typically go with our sodium hydroxide base up at the top here. Much of my rest of my notes here is some pictures here. What I have though here is some terms I need you to know. I think I've already used this word here. Equivalence point. I used that yesterday, right? The word equivalence point. I mean, it it's exactly like you'd think it would be. Equivalence is when you have equal stuff, right? When you have equal acid and you have equal base, that's your equivalence point. Right? So, I need you guys to know this. The equivalence point then is the volume used to make your acid equal your base. When we're talking about a graph, your equivalence point is the volume required that you add, right? Like, so you add a certain amount of titrant from that tube. The equivalence point is how much volume you add. Okay. No, like just how much added there was. So like this right here along this axis here, the volume of strong acid added really is what I probably should say. It's the amount that you like drop in from the remember that burette tool right here? The equivalence point is how much you used. Okay. So that's what goes along one axis. Your equivalence point would be how much volume you used. The other term I have right here is an endpoint. And the endpoint describes the exact same thing. The endpoint describes when you're done your titration. Only in this case right here, the endpoint is the expected pH. And what's the expected pH going to be? Yeah, 7, right? Because we're going to assume that it's going to be neutral. In Chem 30, I'm actually going to show you some exceptions to this rule because that's actually not always at 7. I think I even have a couple of examples later in my notes today. But for right now, hopefully it makes sense, though, that when the amount of acid and base are equivalent to each other, then the pH should be 7 because it's exactly neutral. So if I were to give you a graph, like, I hope I have one here. Perfect. This is one right here. This would be a very typical, what we call this is a pH curve or a pH graph, where you're starting with either acid or base, and it's slowly but surely changing, but then all of a sudden, it goes from being a base to being an acid like immediately. And all it takes is a couple of different drops, like 1 or 2 drops to change like its color change. So this right here, if I were to take this middle point right here and calculate the volume, this would be the equivalence point. So like on this particular graph, if I asked you what the equivalence point is, hopefully you'd say that it's about 24 milliliters. What that means is that if you have your long, thin burette tube, and I ask you to start adding some of your titrant, you need to add 24 milliliters. That's your equivalence point. Does that make sense? The end point then, like I said, is in most cases we're going to work with so far, be 7. So 7 is your end point, and 24 milliliters is your equivalence point. And we're kind of graphing this. Okay, I've talked about asymptotes with some of you guys in math before. Do you guys remember what an asymptote is? How would you describe an asymptote mathematically? Yeah, like it doesn't touch, it gets closer and closer and closer, but it never actually grows any more than that. And that's what these buffering regions are right here. What ends up happening is, let's say you keep adding more and more acid. Will this graph like keep going down and down and down further? Like, will it get to a pH of -1 and then -2 and then -3? No, like at some point it's gonna like limit out and it's really not gonna grow anymore. We call those regions buffering regions, and there's 2 on the graph. Basically, when you're starting to add your titrant, the pH is changing, but it's not changing all that much. Like it's minorly changing. And then over here, once you've actually changed it from being acidic to basic or basic to acidic, then you have the same issue right here. It starts to like level out. So it makes this really funky looking graph like this. Okay. Now, when you're trying to figure out which indicator to use, if you're using an acid being dropped into, or a base being dropped into an acid, phenolphthalein is actually a good choice of indicator. But Rebecca, you are actually onto something here, in that it's actually maybe not the best indicator choice we have because the pH range is a little bit higher than it should be. You actually have to add 1 extra drop in order to make phenolphthalein change color. It would actually be more ideal if we picked an indicator that changes color directly around 7. And so one of the better indicators to use actually would be bromothymol blue. You guys have your data books nearby? Find me the color change range for bromothymol blue. I think I know it, but is it 6 to 7.6? The color change for bromothymol blue? Okay. The reason why bromothymol blue might work better is that as you're adding your titrant, rather than the color change being like a little bit too far, it should be exactly dead center in the middle because 7 is right between those numbers. Does that make sense? So when you're starting, in this example here, it should be blue. And as soon as it turns from blue to yellow, that's when you know you're done. And then ideally, you don't have to add one extra drop. Does that make sense what I'm saying here? Because phenolphthalein changes color a little bit outside of the 7 range, it actually is one extra drop. But here's the reason why we like phenolphthalein. It's very easy to tell when the color changes because it's either clear or it's pink, and there's really no in between. Bromothymol blue, though, will actually go from blue through green to yellow. Does that make sense? What happens if you added one drop, and at first it was blue, and then it was kind of like greenish? Are you done? You know what I'm saying there? So that's one of the nice things about phenolphthalein is it has a 2 color change. It's either clear or it's pink. Almost every other indicator has a 3-way range where it has to go from yellow to green to blue. You know what I'm saying here? So that's one of the reasons why we're okay with overshooting by 1 extra drop on phenolphthalein. So what I've got here then is a list of indicators that change colors at different ranges. And so you can kind of see that if you're looking for something that's going to change color around the 7 range, the best indicator to use is actually bromothymol blue. When I was in university, I did a lab that I used bromothymol blue with. And the most challenging part to it, though, was trying to figure out, is it yellow, is it green, is it blue? You know what I mean? There's a little bit of interpretation. Whereas phenolphthalein is a little bit further, but rather than there being that murky range right here, as soon as you see any pink at all, that's probably a pH of like, say, 8.3. I know it's a little bit high for our equivalence, for our endpoint, but at least it's more definitive, if that makes sense. Yeah, but what happens if it's green because it's at like see how it starts green right here? It could be green because it's at 6.8. It's true. It's true. Yeah. You know, but I mean, it could also be 6.1. I get what you're saying. You know, just phenolphthalein is it's very clear, if that makes sense. Well, I mean, literally. I mean, it goes from clear to pink, and so that makes it very distinctive. So, but that is one of the issues. Is the endpoint is a little bit high. Now, you might say, well, Kristen, why don't we just use that indicator always? But it's actually possible to have a graph that looks like this, where there's actually 2 different little changing places right here. There's actually 2 endpoints. And I've got an example here of one that would do this. It's potassium carbonate and hydrochloric acid. Now, we've covered acids and bases before. I want to try to explain to you guys why potassium carbonate and hydrochloric acid is a bit different. Trying to write the equation first. Potassium carbonate is going to be K2CO3, and hydrochloric acid is HCl. Now, right off the bat, you might say, hang on, Chris, there's an acid right here. HCl, that's an acid, clearly. Is K2CO3, is that a base? Let's revisit our first unit here. What happens to something that's ionic? What can you do with any ionic compound? Well, we can add H2O to it, but before we should do that, anything ionic can be dissociated. So what I could do is I could break this up into K plus and CO3 2 minus. Okay. Now I'm going to take Brady's suggestion. Now let's add water to something. Which one do we add water to typically? Do you guys remember from our first unit? The K plus or the CO3 2 minus? Yeah. So if I were to take that CO3 2 minus and I were to add some water to it, it would form HCO3 1 minus, and it would form hydroxide. There, I now proved that it's a base. Hang on. I'm not done yet. You guys remember this from our first unit here. We can keep going. Because what I could do is I could then take my HCO3 negatives. I could add water to it again. I could form H2CO3 and an extra OH minus. You guys remember doing this from our first unit? It's been a while. The word we used to describe this was called polyprotic. You recall that word at all? Polyprotic. Which basically meant that poly means that it has more than one proton reaction. It has more than one reaction taking place. Well, now use that to explain why this graph looks the way it does. Why are there two little, like, think of it like a water slide. Why are there two little drop-off sections rather than one? Yeah, because it breaks down twice. This base right here actually reacts twice. What ends up happening is the CO3 can react with the hydrochloric acid, but also the HCO3 can also react with the hydrochloric acid. There's actually two reactions taking place. Now, it's a little bit trickier to interpret this, but do you guys see how because there's a double reaction taking place on the base perspective, it actually causes there to be two different equivalence points? Well, what that means then is that if I were to look at these indicators right here, you might say, Chris, just always use bromothymol blue, call it a day. Or you might say, well, always use phenolphthalein, cheat a little bit and call it a day. But what if you're doing a reaction that actually has two equivalence points? Because there's two parts of the base that can react. Well, then you might actually need to have an indicator that changes color around here and around here. So you might actually want to pick an indicator that changes color around, say, 10. So I guess phenolphthalein actually would be a good choice for that one. But you also might want to pick a color that changes color around 4. That makes sense? Which in that case, maybe you might want to pick methyl orange, because methyl orange changes color around 4. So although 7 is the most likely equivalence point, 7 only works if you have equal parts acid and base. Does that make sense? If you have just as much acid as you have just as much base, sure, 7 works. But let me go back to this equation right now. I never actually finished writing out this first equation right here. So I'd like to do that now. If I were to give you K2CO3 and add it to HCl, what reaction is going to take place? Well, it's going to form KCl, because that's going to be right here. And eventually, it's going to form H2CO3, because the H will go with the CO3. But I want to use that word eventually, because in order for it to form H2CO3, it actually goes through a two-step process. First, the CO3 upgrades to an HCO3, and then later, the HCO3 upgrades to an H2CO3. And the reason why I might know that is that I have to balance this guy. And when I balance it, it requires 2 hydrochloric acids for every one of those. Maybe you can kind of visualize this now. The first hydrochloric acid bumps the CO3 up to the HCO3, and the second hydrochloric acid bumps it up to the H2CO3. Does that make sense what I'm saying here? If I were to write this out, I'm sorry that it's such a mess here now, but I'm going to erase mine. I'll try to draw it on the graph better here. Here's what's happening, is that at this point right here, your CO3 2 minus is getting upgraded to an HCO3 minus. And then later at this point right here, the HCO3 minus is getting upgraded to an H2CO3. Does that make sense? And that's why you need 2 different equivalence points. So most of the time, bromothymol blue is a great choice because it changes color around 7. We often use phenolphthalein, though, for other reasons. But if you're doing a reaction that actually involves a polyprotic something, like, say, the potassium carbonate, that K2CO3, this CO3 right here, hopefully you guys understand what I'm saying here, it needs to upgrade from here to here, and then from here to here. In a 2-stage reaction, you might need to pick 2 different indicators. Does that make sense? Okay, now here's what I need you guys to be able to do. This is actually not a hard section. I need you to be able to do 2 things, basically. I need you to be able to look at a graph and tell me what the endpoint and equivalence point is. Okay, now this graph here is not actually labeled all that well, so let's pretend that this was 5 milliliters, this was 10 milliliters, this was 15, this was 20, this was 30, this was 35, this was 40 milliliters. If I were to ask you for the first equivalence point, could you read the graph and tell me that the first equivalence point would be 15 milliliters? Does that make sense? Or if I were to ask you what the second endpoint pH is, you'd be able to say the second endpoint pH is about 4. Okay, so that's one thing. Can you literally just look at a graph and interpret what is happening? Okay. And then the second thing I need you to be able to do is, can you identify an appropriate indicator to use? Okay. One of the uses of indicators that we learned way back when is an indicator helps you narrow down a pH range of any substance. Sure, give me 1 minute, would you? Okay. The other use of indicators now though is to help you find the end point in a titration. Okay, so I just need to be able to figure out the appropriate indicator for that. Okay, go grab some food here. Let's figure out what I have left to do here. Oh, I only have one slide left. Perfect. Okay, so let me do one last example here, and then we'll call it a day. Imagine that in your titration, you put H3PO4 down here in the bottom in your flask. That's the sample you want to titrate. And you want to put NaOH as a base as your titrant. Okay. Now, I'm not really asking you to do any math on this. Okay, the math doesn't change. The whole stoic stuff you do isn't any different. But if I were to ask you to sketch me a graph of what this would look like, here's what it would be. Now, I don't need you to know exactly what the amounts would be. But as you start with H3PO4 and you add sodium hydroxide, what's going to happen is your H3PO4 is going to eventually turn into an H2PO4 minus. Then it'll eventually turn into an H1PO4 2 minus. And then eventually it's going to turn into a PO4 3 minus. Can you guys kind of see the three-stage process that's going to happen here? The H3PO4 and the OH right here, the OH is going to snag one of the hydrogens off of this guy right here. Why is it snagging the hydrogen? What's it forming? Yeah, right. If you can kind of visualize this, one of the H's off of this guy right here is going to attach itself to the hydroxide and make water, which means it's neutralized. Now, normally you'd think, hey, the pH of neutral solution should be 7. But here's the problem. After all of the first H's are stolen off of this guy right here, there's still H2PO4 left. So it's not actually neutral yet. So then more hydroxide steals an H off of this guy to form this one. And then more hydroxide steals the H off of this one to get to here. And now we're finally done because there's no more hydrogens for the hydroxide to form water with. Okay. So if I were to ask you what this graph would look like, if this were a measure of your pH versus the volume of NaOH added, this graph is going to be kind of upside down compared to the ones I showed you on the previous slide. Because what's the pH of the solution in here? If I were to use a pH meter right here to start with here, like a pH meter like this, what would the pH be of, say, NASA when you start? Low. So you'd start off with a low pH. And then what would happen is all of the protons off of the H3, the third proton will leave, and it'll make a point like this. Well, then all of the second protons would then leave. And then that's only got 2 equivalence points, right? But can you guys see how this is H3PO4? This should actually have a third equivalence point. And what's happening is that right here, you started with H3PO4. Here it turned into H2PO4 minus because it lost one of its protons. Here it turned into HPO4 2 minus. It lost its second proton. And then finally here, as you add your base, it's turned into PO4 3 minus, and there's no more hydrogens to be lost. Would bromothymol blue be a good indicator? Actually, it might be for this one right here. If you wanted to find this change right here, I bet you that one's probably in the 6 to 8 range. Right? But you'd need 3 different indicators. You need something that changes color, probably in the 1 to 4 range, 2 to 4 range. You need something that probably changes color in the 6 to 8 range. And you need something that changes color in the 11 to 13 range. Does that make sense? Can you guys see why this graph goes up? Do you get the idea why this graph goes up rather than this graph going down? It's all about who is being added. If you're adding acid to base, you start with a high and the pH starts to drop. Whereas if you're adding, like I had in this picture right here, if you're adding base to acid, then the graph goes up. It's the same graph. It's just it either goes downhill or it goes uphill. It doesn't really matter which one you pick up. So, and hopefully you guys can kind of see that in this picture that I had right here. Here I'm trying to show you all of the different reactions. What you're doing is, I haven't even finished this one. There should be a third equation right here, because what you have happening is it goes from HPO4, H2PO4 to HPO4 to eventually being PO4 3 minus. I just didn't write the third one out for some reason. Do you guys get that concept, though, what I'm saying? Okay, so quick summary of the day. We can then make a graph. On one axis of the graph, we put the pH. We're going to call that the endpoint. On the other axis of the graph, we're going to put how much volume of titrant you add. We're going to call that the equivalence point. Okay. The titrant can either be the acid getting poured in that tube or the base. It doesn't really matter which one it is. In one case, the graph goes down like this. Right? In the other case, the graph goes up. Okay. All you've got to do is figure out whether you're adding acid or whether you're adding base. Okay. Our standard way of doing it in our lab, we're always going to add a base to an acid, and we'll use phenolphthalein. We know that the pH range is a little bit outside of what's expected, but that's actually okay. We'll deal with being off by one drop because phenolphthalein is great because it only goes through one color change. Whereas all the rest of the indicators, it has to go from, like, say, red to orange to yellow. And it maybe isn't quite distinctive because the question is it actually yellow or is it still a little orange? I'm not really sure. You know what I'm saying there? So we like to be very distinctive. Okay. I need you guys to be able to read a graph and interpret what's happening. I need you to be able to, yeah, basically that's it, really. If I give you a graph, can you interpret what's happening? Or I guess maybe the opposite. If I give you a scenario, could you draw me a rough graph of what's happening? Does that make sense? Okay, that's it. I don't actually have any questions on this, by the way, on your assignment. When I give you a quiz question, I'll let you know one of them, by the way. Like, the quiz question is going to be basically this easy. I'm going to give you a graph. All the axes are going to be labeled, and I'm going to say what's the equivalence point. And you're going to look for this point right here. You're going to look down on this axis, and whatever that says, like say 27 milliliters, that's your answer. Okay. It actually is really simple. I might ask you whether you're adding an acid to a base or a base to an acid. So I guess since I'm going here, were we adding an acid to a base or a base to an acid in this example? Yeah, which means if I asked you what the titrant was, you would say the titrant was your base because you're adding a base because the pH is going up. Okay. If you can do that, this is an easy section. So, okay, anybody have any questions? Is it good? Okay. I posted the labs, by the way. If you guys want to maybe grab the laptop, you can print off some class sets for you guys. We'll do our labs tomorrow, and other than that, finish up your old labs or work on your assignment. So no project and no science and society reading this unit. So you don't have to worry about those. Okay.